Welcome back, everybody. This is our second class in NEET previous year's questions for chapter Current Electricity. Before this, in this series, we have made one video, and that video is available on our YouTube channel. We have also started similar series for NEET JEE previous years, so those videos are also available on our channel. You can go and find out those videos in playlist section. And if you find these videos useful, do press the like button, share them, and subscribe to our channel. It helps a lot when you share and subscribe. Also, if you want to support us financially, you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any help, whatever small, will be highly appreciated. With this, let's start today's video. And in previous video, we covered up to question number 30. This was the last question which we covered. And today we will go further. Now, the resistance of a discharge tube is 0 ohmic infinity or non-ohmic. Now, for a discharge tube, voltage versus current graph varies such like this. Variation of voltage versus, we can say, current. It's something like this. This is, we can say, potential, or this is current, or this is potential, this is current. The behavior is something like this. And if a instrument or a device obey Ohm's law, then for that device, V versus I graph is a straight line passing through center, something like this. So this is a ohmic device, and here the behavior we are looking for, or the behavior we are seeing here, this is called non-ohmic behavior, because device is not following Ohm's law, so that's why it's called non-ohmic. So option C is the right answer. Moving to next one. From the graph between I and V shown, identify the portion corresponding to negative resistance. So we just discussed this concept in the previous question, that when a device shows non-ohmic behavior, during this behavior device have negative resistance. And how we can identify negative resistance? We know that V is equal to IR according to Ohm's law, and from that R is equal to V by I. And now in terms of graph, we can write that R is equal to delta V by delta I. Now take point C and D. This is point C and this is point D. So we can say RCD, where C is the initial point and D is the final point. So it will be delta VCD by delta ICD. Delta VCD will be VD minus VC, and ICD will be ID minus IC. Now we know that value of VD on this graph will be something here. Let me draw it with lines. VD will lie here and VC will lie here. And similar for the current, ID will lie here on the graph and IB will lie here. Oh, sorry, IC we have to find out. And IC will lie here. So these will be the points on the graph for corresponding values. And from this, we can see that VD is greater than VC. VD is greater than VC, so this subtraction is positive. But if we see on the current side, then ID is lesser than IC, or IC is greater than ID. So this term, the denominator will be negative, and hence this resistance will be negative. So the non-ohmic region always have negative resistance, and here CD is the non-ohmic region. So option B will be the right answer. If CD is not mentioned here, suppose if CD is not mentioned here, then our answer can also be BD. That as a whole in the BD region we have negative resistance. Moving to the next one. Resistance of a platinum wire at 0 degree Celsius is 2 ohm and 6.8 ohm at 80 degree Celsius. Temperature coefficient of the resistance wire is. So we have to find out temperature coefficient, and we know the relation that R at any temperature theta is equal to R node 1 plus alpha, where alpha is a coefficient of resistivity, into delta theta. Now, normally this R node is at this temperature. R node is measured at 0 degree Celsius. It is a no, that's a normal practice. So, if we write for 80 degree Celsius, R80 will be equal to R at 0 into 1 plus alpha 80 minus 0. R80 is 6.8 ohm, R0 is 2 ohm, 1 plus 80 alpha, and from this will go on 3.4. We will have 3.4 is equal to 1 plus 80 alpha, and from this 2.4 is equal to 80 alpha, and alpha is 2.4 by 80. We can write it like this: 24 into 10 raised to power 1 divided by 8 into 10 raised to power 1. So this will be 3, and alpha will be 3 into 10 raised to power minus 2. Option A will be the right answer. Moving to the next one. As temperature increases, the electrical resistance increases for both conductors and semiconductors, decreases for both, increases for conductor, decreases for semiconductors, increases for conductors, and increases for semiconductors. Now, coming to the electrical resistance, we have to first get an idea that how resistance comes into picture for, we can say, conductors, then for insulators, and then at last for semiconductors. So first let's discuss for conductors. For conductors, what we have? We have free electrons moving around positive ions which are fixed. So in case of a conductor, we have these positive ions which are fixed in the lattice, and we have electrons which are moving side by them, something like this. Electron will move with a zigzag pattern and will reach to the another end. This is the, we can say, basic explanation for conductors. Now, as we increase the temperature, what will happen? As we increase the temperature, then this positive ion will start vibrating, And similarly this lower positive ion will also start vibrating. These both will start vibrating, and when they start vibrating it becomes difficult for this electron to cross them. And as it becomes more and more difficult with more and more temperature, so resistance of a conductor increases with temperature. Now coming to insulators. In case of insulators, these electrons are not free. These are bounded. These electrons are bounded with these positive ions. And we need energy to break them. Now, as we increase the temperature, more and more energy is provided to these electrons, and at sufficient temperature, these electrons will break free from these positive ions. And what we'll have? We have conducting electrons. So resistance for insulator decreases with increase in temperature. It decreases. Now coming to semiconductors. Semiconductors have the same, we can say, same methodology as as of insulators. Just in case of semiconductors, the energy required to break free this electron is more, we can say, quite smaller as compared to insulators, but higher as compared to conductors. In conductors, electrons are free at room temperature, but in semiconductors, electrons are not free at room temperature. We need to provide them some energy, and with very small amount of energy, they becomes free. And so when they becomes free, they start conducting. So again, in case of semiconductors, resistance decreases with temperature up to a limit. After that, what happens? After that, these positive ions of the semiconductors again start vibrating, and again resistance increases. So for semiconductors, if we plot resistance versus temperature, resistance versus theta, the behavior is something like this. That initially resistance decreases, then it start increasing. So increases for conductors and decreases for semiconductors. Option C will be the right answer. Moving to the next one, the solids which have negative temperature coefficient of resistance are insulator and semiconductors, metals. Now, negative temperature coefficient means that their resistance decreases as temperature increases. So, resistance goes down as temperature goes up. And this happens for both insulators and semiconductors. So option C will be the right answer. Moving to next question. Which of the following graph represents variation of resistivity with temperature for copper? Now we have to represent variation of resistivity. Now let's start with resistivity. We know that we have various formulas for resistivity. One of them we can find out using Ohm's law, that V is equal to IR, and we know that resistance is rho L upon A. Now we know that this resistance R is dependent on temperature. And how it is dependent upon temperature? uh, R of theta with in resistance at some temperature theta is equal to R node 1 plus alpha delta theta, where delta theta is change in temperature. Now this law only holds for small changes. According to this laws, that variation of resistance is linear. but actual variation of resistance for a, we can say, some metal is something like this. Initially it is linear and then it becomes exponential because at very high temperatures the positive ions starts vibrating very vigorously and electrons have practically no path available to move or to move to the other point, so resistance becomes uh, very large. Now, as here is no scale is mentioned, so the variation of resistance will be same as variation of resistivity because resistivity is proportional to resistance. For a we can say a wire of fixed length and fixed area, so resistivity is proportional to R, and it will have same variation as has the resistance, and resistance has variation of something like that, that initially these variation are linear, then they becomes exponential, and the closest graph we have, that is option B. And resistivity is actually also defined as resistance of unit length and unit area. So it will follow the same behavior as followed by the resistance in case of with temperature. Moving to next one. Specific resistance of a conductor increases. Specific resistance means rho. So as we already discussed in a previous question that it increases with temperature. So option A increases with temperature. Now coming to the cross section area and length. So it is independent of area of cross section and independent you can say length, because it only depends upon type of material we have. It is fixed for a type of material at certain temperature. So only variation we have is increase in temperature. Moving to the next one. Two heaters X and Y have power rating 1 kilowatt and 2 kilowatt respectively. Those are first connected in series and then connected in parallel to a fixed power source. The ratio of power output in these two cases. So in two cases we have to find out ratio of power sources. So let's divide into two parts, one for the series and one for the parallel. So here we will solve series connection, and here we will solve parallel connection. Now their ratings are given and their power ratings are given, but potential is not given, that at which potential they are rated. So we assume that we are taking a source of, here so a fixed power source is mentioned, so we are taking source at E volts, and their rating we are assuming is also E volts. So we know that power is V square by R. So from this R is equal to V square by P, and using this R1 will be our source potential is E. So E square by P1, that is 1 kilowatt or 10 raised to power 3, and R2 will be E square divided by 2 into 10 raised to power 3. Now when they are connected in series, so total resistance of the circuit will be their combined sum. So RT will be E square by 10 raised to power 3 plus E square by 2 into 10 raised to power 3, and we will get E square by 10 raised to power 3, 1 plus half, that is 3 by 2. So we have the resistance. Now, as we have the resistance, now as we have a series connection, and in case of series connection, we know that current is constant. Now, in case of series connection, current is constant. So what we will do here? We will use formulas of power which includes current. And for that we have to find the value of current, and current will be potential by total resistance. Potential is E by total resistance is 3E square divided by 2000, and 2000 go on the top. So we will have it is equal to 2000 by 3E. That's the value of current we have. Now coming to the power. So P1 will be I square into R1, power of first, we can say that is first heater X. So Px, that is Px is equal to power of first heater, and it will be I square times R1, that is resistance. So I square will be 2000 square into 9E square multiply R1. R1 is E square by 10 raised to power 3. So this from this we will have 4 into 10 raised to power 6 by 10 raised to power 3. E square get cancelled, 1 by 9. So it will be 4000 by 9. This is the power for X. Now power for Y will be I square times R2. So I square will stay the same, and it will be 2000 square, that is 4 into 10 raised to power 6 by 9E square into resistance of second heater, that is E square divided by 2 into 10 raised to power 3. E square get cancelled, and 3. Here we will have 2000 by 9. So total power of Px and Py in the series combination will comes out to be, you can say P total, it will be Px plus Py, that will be 4000 by 9 plus 2000 by 9. It will be 6000 by 9. Now going to parallel combination. We have to find out ratio between series and parallel. So we solved for series. Now we will solve for parallel combination. Now in case of parallel combination, both of these resistances R1, that is of E square by 10 raised to power 3, and R2 E square by 2 into 10 raised to power 3 are in parallel. So potential across them is constant. Now if potential across them constant, what does it mean? Means we have to use a power formula which includes potential. So for that power is V square by R. Now Px will be, potential is E square by R, that is for X the R value of resistance is E square by 10 raised to power 3. So this will give us 1000, and Py will give us E square divided E square into 2 into 10 raised to power 3. So from this we will get 2000. So total power will be Px plus Py is sum of these two values, and it will be 2000 plus 1000, that is 3000. Now we have to find out their ratios. So ratio can be found out that P series by P parallel will be 6000 by 9 divided by 3000, and here from this we will have 2 by 9. Comparing the answers or options, option A 2 by 9 will be the right answer. Moving to the next one, two resistors of resistance 100 ohm and 200 ohm are connected in parallel in an electrical circuit. Ratio of their thermal energy developed in 100 ohm to that of 200 ohm in a given time is. So consider, we are considering, let us consider time t for heat calculations. Why? Because we know that heat is power into time. So we have to take some time, some value of time. Now, as resistors are in parallel means potential across them is constant. So suppose this 100 is R1 and 200 is R2, then it means we can write that P1 is equal to V square by R1 and P2 is equal to V square by R2, make it slightly thicker. And now if we write a ratio of their heats, that H1 by H2, that will be equal to P1 into T multiply P2 into T get cancelled on both sides, and we have P1 by P2, and P1 is V square by R1 and P2 is V square by R2. V square get cancelled and we are left with R2 by R1, and R2 is 200 and R1 is 100, so ratio will be 2:1. Option B will be the right answer. Moving to the next one, which of the following act as a circuit protection device? So basically it's a fuse. Fuse act as a circuit protection device. Next one, a filament bulb 500 watt rated at 100 volts to be used in a 230 volt main supply. When the resistance R is connected in series, it works perfectly and the bulb consumes 500 watt. The value of R is. Now it is mentioned that when some resistance R is connected across it, it works perfectly and consumes 500 watt. Now, working and consuming 500 watt both are different things. Means, suppose we have a 500 watt bulb. It can work perfectly if it is consuming 400 watt, 100 watt, or we can say also 500 watt. In all of these scenario, it will work. But provided that how much power it is consuming, there will be value of current which is flowing through it, and that value of current can't exceed its original rating, because according to its original rating it is rated at 500 watt at 600 volts. Means we know that power is equal to uh, voltage time currents, and for bulb power is 500 and it is rated at 100 volts multiply I, so I is equal to 5 ampere. Means current through bulb, current through bulb can't exceed what we say 5 ampere. If current through bulb exceed 5 ampere, it will get fused. So what we will assume here, that maximum current in this whole circuit where we have a bulb, suppose this is our bulb and a resistance of value R in is series with it, connected to a 230 volt. This is our basic setup. Then this whole circuit value of current can't exceed 5 ampere. Now to find out value of current in this circuit, what we have to find out? We have to find out total resistance of the circuit. We know value of applied resistance is R, and we have to find out resistance of this bulb. That means RP. We have to find out. And for that we can use formula that P is equal to V square by R, and here V is the rated voltage, not the given voltage. Here given voltage 230 volts. Here V is the rated voltage at which power is given, and here a rated voltage is 100 volt and at which power is 500 watt. So 500 is equal to 100 multiply 100 divided by R, and from this R will be 100 by 5, that is equal to 20 ohms. So resistance of bulb is 20 ohms. Here applied, we can say applied potential is 230 volts. Now current in this circuit will be 230 divided by 20 plus R, and as mentioned it can't exceed 5 ampere, so it should be equal to 5. 230 20 plus R is equal to 5. Cross multiplying we will get 230 is equal to 100 plus 5R. From this 130 is equal to 5R, and R will is equal to 26 ohm. And here is the option C will be the right answer. Now we can also validate that second part, that bulb is consuming 500 watt. Now to find out that how much power here bulb is consuming, as this is a series circuit, so we have to use formula for power in form of current, that is I square times R. Value of current in this circuit, that is 5, which we assumed. So 25, 5 square is 25 into resistance of bulb is 20, and multiplying we will get 500 watt. So second, we can say second condition is also satisfied. So option C, R value is equal to 26 ohms. Moving to the next one. Two cities are 150 km apart. Electric power is sent from one city to another through copper wires. The fall of potential per kilometer is 8 volts. Average resistance per kilometer is 0.5 ohm. The power loss in the wire. So we have to find out here power loss, and that we can easily find out that assume this is our wire of 150 kilometer. This total distance is 150 kilometer. Now we are given that there is a potential drop of 8 volt per kilometer. So per kilometer potential drop of 8 volts. Now in 150 kilometer we will have potential drop of, or we can say delta V will be 150 into 8, so that will be 120 volts. So this is the drop of potential, and resistance per kilometer is 0.5. So per kilometer resistance is 0.5 ohm. So total resistance will be, you can say R, that will be 150 into 0.5, that is 5 by 10. It is equal to 75 ohms. So it's like we are having a resistance of 75 ohm, and potential across it between point A and B is 1200 volts. Now how we will find the value of power across this resistance? We can use both of the formula, that we can use either power is equal to V square by R or I square by R. For that I we have to calculate, but as we already have V and R, so we will use this one. So it will be 1200 into 1200 by 75. It will go on 25, it will be 3 4 8, and this will be your 400. So 400 into 48, and if we multiply 8 4 3 8 4 ja 32 and 4 4 16 plus 3 19. So it will be 19200 or 19.2 kilowatt. That is option B will be the right answer. Moving to the next one. Power dissipated in the circuit shown in the figure is 30 watt. The value of R. So total power dissipated is 30 watt. Now as we can see that this system is in parallel. So total power dissipated will be power dissipated in resistance R plus power dissipated in resistance of 5 ohm. Now that should be equal to 30 watt. Now as system is in parallel, so potential is constant. So we will use potential formula for power. Now PR will be put V square by R. So 100 by R plus P5 will be V square means 100 by 5 is equal to 30. This will give us 20. So 100 by R is equal to 30 minus 20, that is 10. And from this R is equal to 10 ohm. Option C will be the right answer. Moving to next one. If voltage across a bulb rated 220 volt and 100 volts. So it is rated 100 watt at 220 volts, drops by 2.5 to its rated value. The percentage at the rated value by which power would decrease. So we have been given change in voltage. So delta V by V into 100, percentage change in voltage is given 2.5, and we have to find out percentage change in power. That we can solve using error analysis. Because change is small, we know that power in terms of potential is V square by R. So delta P by P into 100, resistance will be constant here, so it will be only twice of delta V by V into 100, and this value is given 2.5. 2 into 2.5 is 5%. So option C will be the right answer. Moving to next one. If power dissipated in the 9 ohm resistor in the circuit shown is 36 watt, potential difference across 2 ohm resistor is. So as per mentioned that according power dissipated in 9 ohm resistance is 36 watt, and this is a, we can say, parallel combination of 9 and 6. So potential across both of these will be same. So let's say this is point A, this is point B. So potential across 6 ohm and potential across 9 ohm will be same, and that will be VAB. Now let's use formula for power dissipation. As both are in parallel, so again potential will be same and power will be, formula for power across 9 ohm will be potential across 9 ohm divided by its resistance, that is 9. Now power drop or power consumed by 9 ohm resistance is 36, and potential across 9 ohm is VAB. So V square of AB divided by a value of resistance, that is 9. So from this VAB will be under root of 36 into 9, and that is 6 into 3. Oh sorry, under root will be 6 into 3, that is 18 volts. So value of potential difference between A and B is 18 volts. Now we know potential between A and B. What we can do, we will find out their parallel combination, their combined resistance as a parallel combination. It will be 1 by 9 plus 1 by 6. So LCM will be 18. 2 plus 3, 5 by 18, or 18 by 5. So we can reduce this whole circuit something like this, that here we have point A. Now combined resistance of 9 and 6 is 18 by 5 ohms. 18 by 5. Here we have, this is B point. Here we have potential V, and this is 2 ohm resistance. Now we know potential across A and B, that is 18 volts. So if we know potential across a resistance, we can find out current across it. Now suppose this is current I. As this is a series circuit, current through whole circuit will be same. So value of I across AB, it will be VAB divided by R of AB. Now VAB is 18 and R of AB is 18 by 5. So it is 5 ampere. So value of current flowing in this whole circuit is 5 ampere. Now if we know value of current, this current will go and will we can say will flow across 2 ohm also. And if 5 ampere is flowing across this 2 ohm resistance, then potential develop across it will be V is equal to IR. So 5 into 2 is equal to 10 volts. So option B will be the right answer. And we can also find out value of this V. It will be VAB plus potential across this 2 ohm, that will be 18 by 5 plus 10. So this is approximately 18 by 5. Oh, so that is resistance. Potential is 18. 18 plus 10, 28 volts. So this source is of 28 volt potential. Moving to next one. A current of 3 ampere flows through 2 ohm resistance as shown in the circuit. Power dissipated in the 5 ohm resistance is. So 3 ampere is flowing through 2 ohm. So in this, we can say through this, if we mark some points here, A, B, C, D, E, F. Now as per statement, through wire BC, we have a current of 3 ampere flowing. Now if there is a current of 3 ampere flowing, what we can find out using this 3 ampere, we can find out potential drop across 2 ohm resistance, and potential across 2 ohm resistance will be current across 2 ohm resistance into its value, that is 2. So 3 times 2 is 6 volts. So between B and C, there is a potential drop of 6 volts. Now, as this whole circuit is in parallel, so we can say that VBC means potential across B and C point is equal to potential across A and D point, and is equal to potential across F and E points. So potential across F and E point is also 6 volt. Now let us consider F and E individually, this FE line only. So here we have 1 ohm resistance, and here we have 5 ohm resistance. 1 ohm, 5 ohm, this is F point, this is E point, and we know VFE is equal to 6 volt. Suppose this is there is a value of current I is flowing through this part of the circuit. If we know the potential drop across these 2 points, and we know the total resistance, we can find out value of I, and I will be potential, that is 6 by total resistance 5 plus 1 6, 1 ampere. So there will be current of 1 ampere flowing through this circuit. And if current of 1 ampere is flowing and both are in series, so in series what we use power is equal to I square times R. Value of I is 1 square, R is 5 because we have to solve for 5 ohm. So it will be 5 watts. Option D will be the right answer. Now with this we end this video here. Hopefully whatever we have covered here till now is helpful to you and also understandable. If you have any doubts or suggestion, you can put them in comment section. I will try to resolve or implement. And also, if you like this video, then do press the like button, share as much as possible, and subscribe to our channel. Also, if you like to support us financially, you can scan these QR codes in front of your screen and donate us with whatever amount you want. However small the amount will be highly appreciated. So with this, again, thanks for watching and we will meet in next video.